In episode 35, titled Logs and Exponentials, Why They Show Up in Models and Transformations, the goal is to use logarithms and exponentials to tame scale and growth. Because DataX scenarios often involve skewed data, multiplicative effects, and probability computations that become unstable on raw scales. Logs and exponentials are not just math trivia, they are practical tools that change how numbers behave so models can learn more reliably and so interpretations become more meaningful. When you see huge ranges, long right tails, or relationships that behave like percentage changes rather than fixed differences, log thinking often turns a messy problem into a stable one. When you see rates, hazards, and probability normalization behavior, exponential thinking often explains how models convert scores into meaningful outputs. The exam rewards you when you can recognize where these functions appear, why they are used, and what cautions apply when transforming data or interpreting results. This episode will keep the focus on purpose and consequence, not on algebraic manipulation, so you can apply the concepts under time pressure. By the end, you should be able to choose when a log transform is appropriate, explain what it changes, and describe how exponentials show up in modeling workflows. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A logarithm can be understood as a function that turns multiplication into addition, which is one of the main reasons it supports stability and simpler modeling. When you take the log of a product, you can express it as the sum of logs, and that change from multiplicative to additive structure often matches how real-world processes behave. Many growth processes are multiplicative, meaning a value changes by a factor rather than by a fixed amount, such as revenue growing by 10% or traffic doubling during peak periods. On the raw scale, those changes can look nonlinear and can create variance that grows with magnitude, but on a log scale, they become more linear and more stable. This is why logs appear in models and transformations. They convert a pattern that is hard to model with simple linear tools into a pattern that can often be modeled more cleanly. The exam may not ask you to use the log product rule explicitly, but it will reward you for recognizing that logs turn ratio thinking into difference thinking. When you can state that logs convert multiplicative structure into additive structure, you are capturing the most important intuition. One of the most common practical uses of logs is reducing right skew by compressing extreme values, which helps both reporting and modeling.
Right-skewed distributions occur when most values are small, but a few are very large, which is common in latency, file sizes, transaction amounts, and counts over long windows. Taking a log compresses the high end, meaning a jump from 10 to 100 looks similar to a jump from 100 to 1,000 on the log scale, because both are a tenfold change. This compression makes the distribution more symmetric in many cases and reduces the influence of extreme points on mean-based methods and squared error losses. The exam often tests whether you choose robust methods or transformations when data is heavy-tailed, and a log transform is a classic correct response when the data is positive and strongly right-skewed.
Logs also help visualization and threshold setting because they make variation across orders of magnitude easier to see and reason about.
DataX rewards this because it shows you understand how to make data behavior more model-friendly without pretending the tail does not exist. Exponentials represent rapid growth, and they show up naturally in models that deal with rates, hazards, and multiplicative change over time. Exponential growth describes situations where the rate of change is proportional to the current value, which produces compounding behavior,
like populations, certain failure processes, or cascades of events. In data contexts, exponentials also appear because many models produce linear scores that must be converted into positive rates or probabilities, and exponentials are a standard way to ensure outputs stay positive and reflect multiplicative relationships. The exam may describe hazard rates, event rates, or processes where risk accelerates, and exponential thinking helps you interpret what is happening. It also helps you understand why a small change in a linear predictor can produce a large change in an output when exponentials are involved, because exponentials amplify differences. DataX rewards recognizing exponential behavior because it connects math to real process intuition, which supports correct method selection and interpretation. When you hear compounding, rate, or hazard, you should be ready for exponential reasoning.
Logs also connect to linearizing relationships, which means turning a nonlinear relationship into something that looks closer to linear so simpler modeling can work. If a relationship is multiplicative, such as the outcome increasing proportionally with an input, then logging the outcome, the input, or both can turn that relationship into an additive one. This makes linear models more appropriate and can reduce residual patterns like curvature and heteroscedasticity. The exam may describe a relationship where effects scale with magnitude, such as costs rising proportionally with volume rather than by a fixed amount. And in those cases, a log transform can make the relationship easier to model and interpret. Linearizing is not about forcing the world to be linear. It is about choosing a scale where the model assumptions are closer to reality. This is also why logs appear in many classic models, because they make complex growth patterns tractable with simpler tools. DataX rewards this because it demonstrates an applied understanding of how transformations support model fit and stability.
Log odds in logistic regression are a key interpretation point, and the exam may test whether you understand that logistic regression works in a log odds space rather than directly in probability space. Logistic regression models a linear combination of features as the log of the odds of an outcome, meaning it predicts how the log odds change with a feature change. This is why coefficients in logistic regression are interpreted in terms of changes in log odds, and when exponentiated, they can be interpreted as odds ratios. The exam does not usually require you to compute odds ratios, but it does expect you to recognize that logistic regression is not predicting probability as a linear function. It is predicting log odds as a linear function, and then converting to probability through a sigmoid. This is a classic place where logs and exponentials meet in modeling, because the log transform makes the relationship linear in the predictor space, while the exponential and sigmoid convert back to probability behavior. DataX rewards this understanding because it helps you interpret coefficients correctly and avoid the trap of treating them like linear probability changes. When you can say that logistic regression is linear in log odds, you are at the right level for the exam.
A strong cue for choosing a log transform is when variance grows with the mean, which is a heteroscedasticity pattern common in positive-valued measurements. In many processes, larger values are not just larger, they are more variable, meaning error spread increases with magnitude. On the raw scale, this produces a fan-shaped residual pattern and makes constant variance assumptions fragile. A log transform often stabilizes variance because it compresses large values and turns multiplicative variability into something closer to additive variability. The exam may describe that predictions are much noisier at higher values, or that variability scales with level, and a log transform is a common mitigation in such cases. This is not guaranteed, but it is a well-known and defensible strategy when the data is strictly positive and the process behaves multiplicatively. DataX rewards this because it connects variance behavior to a practical pre-processing step rather than leaving it as a diagnostic observation. When you see variance increasing with magnitude, log transformation should be one of the first options you consider. A necessary caution is that you cannot take the log of 0 or negative values without handling them safely, and the exam expects you to recognize this limitation. Many real data sets include zeros, such as 0 purchases, 0 incidents, or 0 latency counts, and logging those values directly is undefined. Negative values can also appear, depending on how features are constructed, such as differences or signed measurements, and a log transform is not directly applicable there. Safe handling can include using a shifted transform, using a log of 1 plus the value when values are non-negative, or using alternative transformations that preserve sign depending on the scenario. The exam often rewards answers that mention the need for safe handling rather than blindly recommending a log transform for any skew. This is a practical detail that shows you understand transformations as operations with domain constraints, not as generic fixes. When you acknowledge that logs require positive inputs and that zeros need careful treatment, you are reasoning responsibly. Interpreting transformed predictions back on the original scale requires care, because what looks like a small error on the log scale can correspond to a multiplicative error on the original scale. If you train a model on a log transform target, the model's output is on the log scale, and converting back involves exponentiating, which can reintroduce asymmetry and amplify differences. This means you must be cautious about how you summarize errors and how you communicate expected outcomes, because the mean of log values does not directly become the mean on the original scale. The exam may not ask you to do bias corrections, but it may test whether you understand that back transforming changes interpretation and that you should evaluate and communicate on the scale that matches the decision. For example, if stakeholders care about percentage error, the log scale can align well, while if they care about absolute units, you may need to translate carefully. DataX rewards this awareness because it prevents a common mistake where transformed model outputs are reported as if they were raw units. When you remember that transformation changes the meaning of error and predictions, you choose safer communication. Log scale is also useful for comparing ratios and percentage changes naturally, because differences in logs correspond to ratios in the original scale. This means a constant difference on the log scale corresponds to a constant multiplicative factor, which aligns with how growth and decline are often experienced in business and operations. If you care about relative change, such as a 10% increase, log thinking makes that change additive and stable across scales. The exam may describe comparing growth rates, analyzing proportional changes, or evaluating performance across orders of magnitude, and log scale is often the right lens. This is also why log transforms can make relationships more linear when effects are multiplicative, because linear changes in the predictor translate into multiplicative changes in the outcome. DataX rewards this because it shows you can choose a scale that matches the meaning of the problem, not just the convenience of a method. When you can say that logs make ratio thinking easier, you are using the concept correctly. Exponentials also appear in softmax and activation functions conceptually, because exponentials are a standard way to convert raw scores into positive values that can be normalized into probabilities. Softmax takes a set of scores and exponentiates them, then divides by the sum, producing a probability distribution across classes. The purpose is to turn unconstrained scores into positive values that reflect relative strength and then normalize them so they sum to 1. The exam may mention multi-class classification outputs, probability normalization, or scores converted into probabilities, and softmax is a common mechanism behind that description. Exponentials are also used in activation functions and in modeling rates because they guarantee positivity and create smooth, differentiable transformations. DataX rewards this recognition because it connects exponential behavior to how models produce interpretable outputs. When you understand that exponentials expand and convert scores into positive, unnormalized weights, softmax becomes intuitive rather than mysterious. Logs also support numerical stability in probability computations, which is a practical reason they appear in algorithms and in exam discussions about computation. Probabilities can become extremely small when you multiply many of them, which can cause underflow in numeric representations, making values round to zero. Taking logs turns products into sums, which are much more stable numerically, allowing computation to proceed without losing information. This is why many probabilistic models, likelihood computations, and training objectives are implemented in log space, and why log likelihood is such a common term. The exam may frame this as avoid underflow or improve numerical stability, and the correct explanation often involves using logs to convert multiplication into addition. This is also why softmax computations are often stabilized using log-based tricks, because exponentials can overflow and logs can help control scale. DataX rewards this because it shows you understand logs as computational tools, not just statistical transformations. When you can state that logs prevent underflow and stabilize probability calculations, you are reasoning at the right level. A useful anchor for this episode is that logs compress and linearize, while exponentials expand and convert because it captures their complementary roles. Logs compress large ranges, reduce right skew, and turn multiplicative relationships into additive ones, which supports stable modeling and interpretation. Exponentials expand differences, represent compounding growth, and convert linear scores into positive rates or probability weights, which supports interpretation in rate and classification settings. Under exam pressure, this anchor helps you quickly choose which function fits the situation, such as using logs when scale is wild and using exponentials when you need positivity and conversion from score space to probability space. It also helps you remember the caution about inputs for logs, because compression only applies when the domain is appropriate. DataX rewards this anchor-driven clarity because it produces consistent choices across transformation and modeling questions. When you can articulate both roles cleanly, you reduce confusion and improve speed. To conclude episode 35, choose one transform case and then describe how interpretation changes, because that is the exam skill that prevents careless reporting. Pick a scenario like modeling latency, where values are right skewed and variance grows with the mean, and explain that a log transform compresses extremes and can stabilize variance, making modeling more reliable. Then explain that predictions on the log scale represent multiplicative changes on the original scale, so differences correspond to ratios and errors correspond to relative factors rather than raw unit differences. Add the caution that zeros and negatives require safe handling and that back-transforming predictions requires careful communication so stakeholders do not misinterpret log-scale outputs as raw values. Finally, tie the choice to the purpose, such as reducing skew, improving stability, and aligning the model with percentage-based decision needs. If you can narrate that interpretation shift clearly, you will handle DataX questions about logs and exponentials with confident, correct, and professionally defensible reasoning. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.